Have you ever wondered why things fall towards the ground? Why the planets circle the sun? Why we don't simply drift off into space? These questions, my friends, have been the subject of human curiosity for centuries. The answer, as science has long told us, is gravity. Gravity, as traditionally understood, is a force between objects with mass. It's what keeps us anchored to the ground, preventing us from floating away into the abyss of space. It's what makes an apple fall from a tree, a stone drop from your hand, and it's what makes you weigh, well, what you weigh. When you step onto a scale, the number you see is a representation of the Earth's gravitational pull on your mass. It's gravity that's pulling you down, giving you weight. And it's not just about you and the Earth. This fundamental force is at play everywhere in the universe. Take our solar system, for example. The sun, a massive ball of hot, burning gas, exerts an enormous gravitational pull. It's this pull that keeps the planets, including our Earth, in their orbits. Without the sun's gravity, the planets would simply shoot off into space in a straight line. And then there are black holes, those mysterious cosmic entities with a gravitational pull so strong that nothing, not even light, can escape once it gets too close. So, the force of gravity seems straightforward enough, right? It pulls objects towards each other, the strength of the pull depending on the mass of the objects and the distance between them. It's a simple, neat and tidy explanation. But what if I told you that gravity, as a force, is only a small part of a bigger, more complex phenomenon? What if I told you that our understanding of gravity, as laid out by Sir Isaac Newton more than 400 years ago, is not the whole story? What if there was more to gravity than meets the eye? Well, there is, and to understand that, we need to delve into the world of Albert Einstein and his general theory of relativity. But that, my friends, is a story for another time. Enter Sir Isaac Newton, a towering figure in physics. The apple falling on his head? A myth. But the contemplation of a falling apple? That's truth. Now let's dive into Newton's theory of gravity. Newton observed an apple falling from a tree and wondered why it fell straight down and not sideways, or in another direction. This led him to propose the idea of a gravitational force between two bodies, pulling them towards each other. The strength of this force, he suggested, was directly proportional to the mass of the bodies and inversely proportional to the square of the distance between them. This idea was revolutionary. It suggested that the path an object would take under the influence of this force would be the shortest one possible, in order to minimize the use of energy. In other words, a straight line. This is why, according to Newton, an apple falls straight down towards the ground. The gravitational force accelerates it in that direction. But Newton's theory had one intriguing quirk. He originally thought of the force of gravity as a push, not a pull. It was an idea that didn't quite fit with his own theory, but it was left as a loose end. Despite this, his theory of gravity was widely accepted. It was a simple, elegant explanation for a phenomenon we experience every day. And so, Newton's theory persisted. For 400 years, it was the accepted explanation for why things fall to the ground, why the moon orbits the Earth, and why the planets orbit the sun. It was, to put it simply, the way the universe worked. Or so we thought. But then, another genius entered the scene. Scene script. Meet Albert Einstein, another giant of genius. In 1905, working as a simple Swiss patent clerk, he presented his general theory of relativity. Einstein's theory was a bold challenge to Newton's, proposing a radically different understanding of gravity. Initially, his ideas were either ridiculed or simply ignored, as they seemed utterly impossible. Einstein's theory suggested that gravity was not a force pulling objects together, but a warping or curving of space and time around objects with mass. Picture a large bowling ball resting on a trampoline. The weight of the ball causes the trampoline to sag or curve. If a smaller ball is placed on the trampoline, it will roll towards the larger ball, not because of a force pulling it, but because of the curve created by the larger ball. According to Einstein, that's how gravity works. This was a radical shift from Newton's theory. Newton's apple didn't fall to the ground because of a force acting upon it, but because the mass of the Earth warped the space around the apple, causing it to move along this curve. But here's the crux of Einstein's theory. Everything in a gravitational field falls at the same rate. It doesn't matter if it's a feather or a rock. If there's no air resistance to slow things down, they will hit the ground simultaneously. This was a surprising prediction of Einstein's theory, and it took many years for technology to advance to a point where it could be tested. The Apollo 15 mission in 1971 did just that. Astronaut David Scott performed a live experiment on the moon, dropping a feather and a hammer. With no air resistance, they fell at the same rate and hit the lunar surface simultaneously, thus confirming Einstein's prediction. But Einstein wasn't the first to conclude that all objects dropped in a vacuum fall at the same rate, regardless of their mass. That insight actually came from Galileo centuries earlier. But it was Einstein who explained why this happens, turning our understanding of gravity on its head. Galileo was the first to conclude that all objects dropped in a vacuum, absent an atmosphere, fall at the same rate, regardless of their mass. Now, let's dive into this insight, which is a cornerstone of our understanding of gravity. Picture Galileo dropping two different objects from the Leaning Tower of Pisa, expecting them to land at the same time. While this experiment is more of a legend than a historical fact, it beautifully illustrates the concept. Galileo was challenging the conventional wisdom of his era, which held that heavier objects would fall faster than lighter ones. Fast forward a few centuries to the Apollo 15 mission on the moon. Astronaut David Scott carried out a live experiment reminiscent of Galileo's idea. He held out a hammer and a feather and dropped them at the same time. In the absence of air resistance, they fell at the same rate and hit the lunar surface simultaneously. This televised moment was a poignant confirmation of the principle Galileo had proposed so many centuries before. This principle is known as the principle of equivalence. It states that all objects in a given gravitational field experience the same acceleration, regardless of their mass. In other words, gravity affects everything equally. This is quite a radical departure from our everyday experience, where air resistance can make a feather fall slower than a stone. But remove that air resistance, and they fall together. The principle of equivalence is one of the key ideas in Einstein's general theory of relativity. It's a simple idea, but it has profound implications for our understanding of the universe. It tells us that gravity isn't about objects with mass pulling on each other as Newton proposed. Instead, it's about how mass warps the fabric of space and time around it. So, why do all objects fall together and hit the ground at the same time? The explanation is they are not falling, they are actually at rest. There is no force acting on them. This might sound counterintuitive, but it's the cornerstone of Einstein's theory of relativity. You see, in Einstein's universe, gravity is not a force acting between two objects with mass. Not at all. Instead, gravity is the curvature of space and time in the presence of objects with mass. Imagine, if you will, a large rubber sheet stretched out. If you place a heavy ball on that sheet, it will create a dip, a curve in the rubber. Now, if you roll a smaller ball near the edge of that dip, it will move towards the heavier ball, not because there's an invisible force pulling it, but because the rubber sheet, the fabric of space and time, is curved. But what does this mean for objects in our universe? Well, without a force acting on them, objects will follow a straight path in space. Yes, you heard that right, a straight path. But this isn't your everyday straight line, it's the shortest path in a curved space, what we call a geodesic. It's like flying in an airplane. Though the shortest distance between 2 points on a globe is a straight line, when you lay that line on a map, it appears curved. That's a geodesic. So when we see an object moving in a gravitational field, whether it's an apple falling from a tree or a planet orbiting a star, it's not being pulled by a force. It's simply following the geodesic in the curved space-time around the mass, creating the gravity. So next time you drop something, remember, it's not falling. It's simply following the curvature of space-time. Gravity is not a force, it's a path.